Hello everyone. In this video, I will explain the algorithm for implementing sampling based MPC using the model predictive path integral update rule. First, I will quickly discuss what model predictive control is. There, in using model predictive control, we predict the controls for each time steps into the future using a simplified model of the robot. So let's say we have a circular robot like this. These are the wheels, and let's say we are representing this using the unicycle kinematics model. So the equation for the so let's say the current state of the vehicle is represented by x0, y0, and theta 0, where x0 is the x position of the vehicle, y0 is the y position of the vehicle, and theta 0 is the orientation of the vehicle. So the um, next state of the vehicle will be represented by these equations. X1 will be x0 plus v1 cos theta 1 dt, y1 equals y0 plus v1 sine theta 1 dt, and theta 1 equals theta 0 plus w1 dt. Here v1 is the velocity at time step 1 and w1 is the angular velocity at time step 1. um, when using model predictive controls, we will try to predict this v and omega for say h time steps into the future, and we'll predict this controls based with some constraints on them, like there will be some acceleration bounds on the way on the controls. Also, the robot will have some upper limit and lower limit on the vehicles, like they can't move beyond a velocity of 10 meters per second. Keeping all these constraints in mind, we will always try to predict the controls. In sampling based MPC, what we do is we sample the controls from um, in sampling based MPC, we sample the controls from a Gaussian distribution, and again we roll them out using the unicycle kinematics model and score them each of the trajectory based on the cost functions. So the cost functions can be obstacle avoidance or lane boundary cost and smoothness cost and goal reaching cost. So in the last class I showed you how to implement the SMPC using the cross interval method update rule. The algorithm is you sample n controls for each time steps into the future from a single Gaussian distribution. Then you clip the controls according to the control bound for the robot. That is, you make sure that the sampled controls are within the upper and lower limit of the agent. We roll out all the trajectories using the unicycle kinematics model, and we score all of the trajectories using these three cost functions. Then we select the elite trajectories, and the new mean will be the mean of these trajectories, and the new variance will be the variance of the new trajectories. The implementing the SMPC with the MPPI update rule is almost the same with some minor difference, mainly the update function. Um, you are going to implement this for your assignment. In the class, I have showed you how to sample from a single Gaussian distribution. In this case, you will have one Gaussian distribution for each time step into the future. So suppose you're predicting a trajectory for 30 time steps into the future, then you will have 30 Gaussian distributions. So at time step 1, you will sample n controls from the Gaussian distribution 1. At time step 2, you will sample n controls from Gaussian distribution 2, and so on. Okay, so let's look at a simple example on how to sample controls from multiple Gaussian distributions. Let's say in our case h is equal to 3 and n is equal to 2. So we'll have Gaussian distribution 1, Gaussian distribution 2, and Gaussian distribution 3. Now from Gaussian distribution 1, we will have uh, V1 W1, V2 W2, V3 W3. I'm going to call this V11 W11, V12 W12, V13 W13. Similarly, from Gaussian distribution 2, we'll get V21 W21, V22 W22, and V23 W23. And from Gaussian distributions 3 we'll have v31 w31, v32 w32, and v33 w33. Now, we know the current state of the vehicle at time step 0, which is represented by x0, y0, and theta 0. So, uh, this, sorry, this this represents time step 1, this represents time step 2, and this represents time step 3. At time step 1, and this is sample 1, this is sample 2, and this is sample 3. In time step 1 we get the position state of the vehicle or the agent using sample 1 by passing this value through the unicycle model, and then in time step 2 using sample 1 we will get the state of the vehicle using the unicycle model after passing these values will be x11, y11, theta 11. Similarly, we will pass these to this state to get the next state x21, y21, and theta 21. And for time step 3 also like this we will get. Similarly, again in time step 1 using sample 2 we will get x 12, y12, and theta 12. And similarly, for time step 2 using sample 2 we will apply this to get x 22, y22, and theta 22. This is 2 only, right? Yeah. And we will then use this on this to get x3 32, y32, x32, y32, and theta 32. Like this we will roll out, so we will get 3 trajectories like this. So I hope the sampling is clear. If it is not clear, just leave a comment in the course portal and I will again get back to you. Once we sample all the controls, we will roll out using the unicycle model like I showed here. And the trajectories will be looking somewhat like this. Now from here we have to score all the trajectories and select the top trajectories. Let's see how we're scoring. We're using I am showing here 3 cost functions. One is the road boundary cost, the obstacle avoidance cost, and the smoothness cost. The road boundary cost makes sure that if there is a boundary of the road, we want to stay within the road boundary. So in this case, after sampling, these are the trajectories I'm getting. Whichever trajectory is lying outside the road boundary, I'm giving it an extremely high cost. And if the trajectory is lying within the road boundary, it is getting 0 cost. In this case, the trajectories with extremely high costs are represented with red, and the trajectories with 0 cost are represented with green. When selecting the elite trajectories, we will be selecting the trajectories from amongst these green samples. This is the obstacle avoidance cost. This is what I discussed in the last class. In this case, as you can see, there is an obstacle here, and I want to select trajectories which are not colliding with the obstacle. The obstacle avoidance function is a standard Euclidean distance function. We want to make sure that the Euclidean distance between the centers of the ego vehicle and the obstacle is greater than the sum of their radius. In this case, the green trajectories are not avoiding the obstacles, whereas the red trajectories are avoiding the obstacles. We want to select the trajectories from these green samples. And the smoothness cost. This is also something I discussed in class. We want to make sure that the trajectory is not very jerky. So if there are no obstacles, the trajectory, there should be very minimal change in the angular velocity of the vehicle. In this case, it is represented by this function, and as you can see here, all the most straight trajectories are having the most lowest cost, which are represented by the green color, whereas the trajectories with higher cost are represented by the red color. Now we calculate the total cost by summing all these costs, and uh, we will select the trajectories based on the total cost. Okay, so now coming to the update rule. Uh, we have H Gaussian distributions, right? And we have to update each of them separately based on the cost functions of all the n trajectories that we got. So to recap, let me just remove this. To recap, we sampled n trajectories. From here, we selected, say, top k trajectories, which we are representing with the color blue. Let's call this trajectory 1, trajectory 2, and trajectory 3. Trajectory 1's, we after we score them, let's say trajectory 1's cost is equal to 10, trajectory 2's cost is equal to 5, and trajectory 3's cost is equal to 100. Now we want to update the mean and variance of each of the Gaussian distribution based on the controls that lead us to these trajectories. So let's say h is equal to 3, let's say h is equal to 3. So we have 3 time steps, t equals 1, t equals 2, and t equals 3. Yeah, so this is t equals 0, and this is the current position of the vehicle. Now this all these three samples are sampled from Gaussian distribution 1. Similarly, these ones are sampled from Gaussian distribution 2, and these ones are sampled from Gaussian distribution 3. So G1 has mu1 and variance 1, G2 has mu2 variance 2, and G3 has mu3 and variance 3. So once we get the cost of all these three trajectories, we want to update mu1 based on this. What we do is we first calculate the exponential utility of these trajectories. So what does the exponential utility function does? So we have three trajectories marked by trajectory 1, trajectory 2, and trajectory 3 with cost 10, 5, and 100 respectively. The exponential utility function will basically be very small for trajectories with higher costs and larger with trajectories with lower cost. So W1, W2, W3, let's say, um, using this formula for trajectory 3, the exponential cost will be very, very low. Then, and for trajectory 2, which has the smallest cost, the exponential utility will be very high. Trajectory 1 lies in the middle, so it will be somewhat like this. I have not calculated these numbers. These are just, I'm placing them arbitrarily. Here beta is a hyperparameter. It's you like chosen by the user. Generally as a norm, people keep it as 0.99. Okay, so once we have the exponential utility of all the trajectories represented by W1, W2, and W3, what we do is we find the softmax of all of these exponential utilities. So softmax is represented by this symbol. It is given by the formula Wi by summation of Wii equals 1 to k, since we have k trajectories. So this represents this will give us the probability of Wi happening. So if W3 is for, let's say, for the softmax for W3 will be very less because W3 is very less, whereas the softmax for W2 will be very high because W2's exponential utility is very high, and the sum of the softmax of W1, W2, and W3 will always be equal to 1 because it represents a probability distribution. Let me just erase this part. Let's say we have the softmax for W1, W2, and W3. Um, let's say this is 0.0004, 0.99, and this will be something like just calculate and figure it out. Anyways, we will have these now at time step h, small h, uh, for say control 1, we multiply it. Control 1 is represented by this one, which has this cost, and its exponential utility is represented by w1. So its softmax 1, we will multiply it with it, and for control 2 we will multiply this with uh, its softmax of w2, and for control 3 we'll multiply this with its softmax of w3. So this way we get a weighted sum of all the three controls that we got from Gaussian distribution 1, which is the new mean. But instead of using that as the mean, what we do is we have this alpha mu parameter, which we call the mean step size. We move take like this. So let's say this is 0.9, which means we take 90% of the new mean plus 10% of the old value. So the new updated mean will be in between the old value and the current value. We do this so that we want to make sure that there is not a sudden change in the new mean. Like this, we also similarly find the variance and update the variance. Alpha mu and sigma are hyperparameters that the user has to define. Generally, alpha mu is kept as 0.9 or 0.7, and alpha sigma is kept low at 0.2 or 0.3. But again, depending on the use case, you have to change all these and experiment with different values and see what is working for you. So this is all for the model predictive path integral update rule. Here I am showing for different alpha mu step size. So we can see that as alpha mu increases, um, we are moving closer to the goal points. The goal point is represented by this cross. With alpha mu 0.1, we are not moving that fast, whereas with alpha mu 0.9, we're moving very fast towards the goal point, because the mu's are changing very quickly. And here I'm showing for sorry how the trajectory varies as I change the step size of alpha sigma. So as you can see, for very small the variance is larger, whereas for very high value 0.5, almost all the samples are lying together and it looks like almost one single trajectory. So this is all there is. Now this is your assignment. You will sample n number of trajectories for each time steps. For each time step you will have a different Gaussian distribution. um, like I discussed in this video how to sample from there. You will score each trajectory with these three cost functions. These three cost functions I have already shown you guys how to do in the CEM class. I have also coded it, and then you will update the cost function, mean and variance of each of those distributions using the MPPI update rule. You will also answer these three questions. The answer to these three questions can be found in these two papers, so just go through them. And if you have any questions or any doubts in this video, just leave a comment or ask me in the next class. Thank you.